It's In Code We Trust, and today we're going to tackle one of the blind 75 problems on LeetCode. For those of you who are not familiar with it, I'm going to have a separate video on this topic, but essentially it's a carefully curated list of 75 problems from LeetCode, curated by Facebook lead, tech lead, who supposedly, like the list supposedly cover like all the aspects and topics of technical interview question you can encounter during your interviewing process. So I'm going to do it a little bit differently. It's a LeetCode problem, but we're not going to solve it in a LeetCode. By the way, I'm going to have a link in the description for this problem in LeetCode. But essentially, what we're going to do is we're going to try to do it in I don't know, more of a actual interview settings, because for your interview, nobody's going to ask you to open up a LeetCode and like have a full description of the problem with images, with examples, and your constraints, like test cases and stuff like that. What's going to happen in actual interview is probably pretty much like a Google Doc settings, where you'll have a short description of the problem. And you're going to go from there, right? So that's with that being said, let's move on to the problem. Right, let's try to tackle this problem. So we are given this description at the top. Let's read it. Given a reference of a node in a connected undirected graph, return a deep copy clone of the graph. So, okay, so we have a couple things here. We know that the graph is connected and it's undirected, and we need to like create essentially pretty much like we need to copy every node of it, create a clone of it, and connect it in the same way it was connected in the original graph. Like just like in an image, you're given an original graph. You want to create a whole new graph that looks just like it, right? So okay, and then you are given a definition of a node. It's a class with a property integer val with neighbors, array of optional nodes, and you have this nice constructor. Okay, looks good. Now you want to try to like come up with a solution, right? So now you need some structure for your technical interview, how you're gonna structure your thought process, how you're going to go throughout the interview. So the one that I use, and I share it in a separate video, I'll put a description to it. But essentially, the first step is collect information about the input and think about the edge cases, because in a setting like this, you're not given any constraints. You don't know about the input. It's very different from the one that you get in a LeetCode, right? Because part of the reason is that because the interviewer wants to have a conversation with you, right? You need to be able to ask questions, ask the right questions, to collect all the information necessary to solve this problem. So it's always be the case. I think it's always going to be the case that you'll not be given all the information you need to solve the problem right away. Part of the interview is to check if you can ask the right questions and collect the missing information right from the interviewer. So with that being said, let's think about this step. What questions can we ask here? So it's a graph problem, and we need to think about the edge cases. And the simplest edge case is, what if the input is empty? What is if the graph is empty? What if it's all negative? I don't know, just some examples of the questions you can ask, but obviously you have to filter them to be relevant for the problem given. But for this one, I think the one of the first questions you can come up with: what if the node reference you are given? So it says you're given a reference to a node. What if it's nil, right? What if the original graph is empty? What do you return? What do you do then? So what if it's nil? Do you return 0, or do you return an empty array, or do you return I don't know, -1? There are several options for this problem. I think you can return nil, right? So that right away gives you some information. So you have an idea what's your method declaration is going to look like, right? And the next question I could think of is, so okay, you're given this graph, you need to create copies of it. But so as you traverse the graph, right? So it's undirected. Probably you're going to use one of the traversing algorithms for the graph. It can be BFS or DFS, but essentially what you need is somehow differentiate if you have created a copy of this node already. For example, we are at node 1, we traverse all its neighbors. Let's say we went to 2, we created a copy of 1, we went to 2, and at 2 we want to create a copy of it, and then traverse all its neighbors, and we see that 1 is also a neighbor of 2, right? So at this point we need somehow to be able to tell if we have already created a copy of one or not. So a valid question here would be, how do we like what's it like what is the unique value of the node? Like how can we differentiate between different nodes? Is it the case that this property value integer is unique for every node, as in this picture right here? Yeah, because it might not be actually, and depending on that information, your approach is going to be different approach to solve the problem, right? So yeah, so probably for this example, you can assume that your interviewer is going to go ahead and say that, yes, actually the value is going to be unique and for every single node. So that's how you can differentiate if you have already created a copy of that node or not. So, but this again is it's very important questions to ask, and it shows your interviewers that you can ask the right questions, think through the problem, and not just go ahead and assume like things you don't know and like do it your way. It's always like a conversation, so you need to be like, it's always a good idea to start with collecting the information about the input. So that's the first step. Let's move on to the next one. So the next step is outline the approach. It is actually very important. Only after we collected all the information necessary to tackle the problem, we can go ahead and try to think out loud throughout the problem and some of the ways we can solve it. So for this particular problem, we see it's a graph problem, so it's already kind of give away that we might end up using one of the graph algorithms. It can be DFS or BFS. Dexter, in this particular example, that would make any sense because the graph is not weighted. We don't have weights for the edges, and the problem has nothing to do with like shortest path or anything like that. So we can narrow down our search to those two, breadth first search and depth first search algorithms, right? But it's not enough just to say, oh, we're going to use depth first search for this problem, because it involves a little bit more work than that. So we need to actually like go through every step of the algorithm and like try to describe it, so you fully understand your approach, and your interviewer does understand it too, so you are on the same page and can move on to the next stage. So here, my way to think about this problem is, so okay, we have this graph, we start from one node, and we need to create a copy of it. And once we create a copy and then we go through its edges, like visit other nodes. First, we need to know how, like if we have already visited this node on, and second, we need to know have we created the copy of this node, right? So probably one way to do that would be, and we also know that the value property is going to be unique for every node, so that's one way to differentiate between nodes. Probably we can use some data structure to be able to tell if we have visited the node and if we have created a copy of it. So and again, like at every single step, let's say we're at a node 2, we're looking through its neighbors, and we already processed, like we already created a copy of 1. We're at this node 2. First thing to do would be to create a copy of it and then look through its edges and see, like we see that, let's say we'll go this way, see that one of the edges is to the node 1. And so we created this copy, and we want to create this edge. But we want to create this edge not between the original node 1, but with a copy of node 1, right? So we, as I've mentioned, we can create a separate data structure for the copies, and we need to actually access the copy node. And so for every node, we need to be able to access its neighbor's copies, and one of the data structures that allows a very fast access is a hash map or a dictionary. So we can use that, and then we're going to say like, okay, so we had let's say we started with 1, we created a copy of it, go through all its edges. Let's say we're at 2, and we check first if 2 is already in our dictionary of visited nodes. If it is, it means that we have created a copy of it. If it's not, it means that we need to create a copy of it and put it in a visited, right? So after that, we need to decide like how we're going to traverse it, right? So we have two options as depth first search or breadth first search, and here you can like say that like describe both ways, or pick one and then ask if like your interviewer has any preferences. You can like go ahead and use that approach, or if or he or she doesn't have any preference, you can use whichever you're more comfortable with, right? So for this problem, I'm actually going to solve it in both ways, but for this first video, let's do it in a depth first search way. So let's say we are at this point two. We always like trying to go in depth, right? So at this point two, I'm going through all its neighbors, and I see that one of the neighbors of two, original two, is one. So I want to create an edge between my copy 2 and 1, but I want to create it between the copy of 1, but not the original one. So I'm going to go ahead and check if I already created this copy for node 1 in my data structure. Like you can put probably like, because we need to fast access to the data structure, we need to be able to say quickly if we already visited or not. We can use dictionary, and the key can be actually this value integer int, and then the value of this dictionary can be node, right? So again, at this point too, we want to check our dictionary. If we have already like created a copy of it, I want to create an edge between. I want to add 1, but I want to add copy of 1 to my neighbors of copy of 2, right? So I check it in a dictionary. If I do have it, I get the copy and add it to neighbors. If I don't have a copy of 1, I'm going to go ahead and create a copy and then add it to neighbors. So, but for the case of 1, it is a case that we have already created a copy. But if we go ahead and check the next edge of 2, is 3, right? We see 3, and we want to create an edge between copy of 2 to the copy of 3. So we're going to check our dictionary. Does it contain a copy of 3? And we see that it's not, because it's not been processed yet. So we're going to go ahead and create a copy of 3 and then put it into our neighbors. After that, I'm going to proceed to the 3. Proceed to the 3 and do essentially the same thing, right? So after outlining like a couple of those steps, and the key actually here is to use dictionary or any like other data structures that allows you to quick access to the node. Like you need a separate data structure to have hold your original, to differentiate between your original graph nodes and your copies. So after you outline a couple steps, you can go ahead and ask your interviewer, does like your approach make sense to him or her? Does he or she agrees with it? And if your interviewer does agree with you, you can go ahead and like move to the next step. All right, so the next step is very important to bring the step out first, and not wait to for the interviewer to ask you to estimate the time complexity and space complexity of your approach. So here for the outline, I can actually go ahead and mention that I'm going to use like DFS, or I can also use BFS here. So yeah, again, estimating time complexity and space complexity, all those FAANG companies, they really care about the performance. So it is very important to show your interviewers that you care about it too, and you know how to estimate those things. Here you're gonna say that, okay, so now based on your outlined approach, you're gonna use the dictionary, and so you can just like write TS stands for time complexity, and SC stands for space complexity. You can say, okay, so we are using like to traverse this graph, we're gonna use DFS, which has time complexity big O of E plus V. And you need to describe what is V and E stands for. Like in this case, E stands for edges. You have like in this example, how many edges is it? 4. 1, 2, 3, 4. 4 edges, and you have 4 vertices, right? So this is it's connected graph, so it's going to have the same amount of but this very particular example has the same amount of edges as vertices, but it can be a case that like one is connected to every single, it's like a tree, one is connected to every edge, and that's the only connection. So in that case, like, you're going to have like v-1 edges, and like you can have every edge connected between each other, and that in that case you're going to have like more edges and vertices. But overall, like overall time complexity for breadth first search is, or depth first search, I should say, and breadth first search is E plus V. And then, but when it's not all, for we need to think, right, for every we need to visit every node, and for every node we're gonna ask ourselves, do we did we already created a copy of it or no? But and we're gonna look it up in our dictionary, which has like a lookup time complexity big of 1, so it's constant, so it doesn't add space time complexity, but it is again like kind of important to mention that you and for your own benefit, it is like important to think throughout every single step, so you are sure you didn't miss anything. And for space complexity, you you you'll be using this additional dictionary to look up if you have already created a copy of your node. And apart from that, DFS doesn't require any additional memory, so it's just going to be E of V, right? V being your nodes. So and you can actually go ahead and say, like in the comments or somewhere, say V stands for vertex, and E stands for edges. Number of vertices and number of edges. And then after that, you're gonna go ahead and ask yourself, actually, like, can I do better? Let me think, like, if I can do better or not. Probably for this example, as you need to create exact copy of original graph, so you would need to go through every single node and its edges at least one time to be able to recreate it. So that time complexity is actually the best you can do. So just mentioning it, you can like ask if he's okay with it, and you can proceed to the next step, which is coding. We go jump to the code. Let me quickly mention that standard implementation of DFS and BFS would actually require some additional memory, but it would require to store visited nodes in an additional data structure, so it's going to require additional O of V memory. But in this case, we're going to use that same dictionary we have created to be able to differentiate, like, if we have visited it or not. So overall space complexity would stay the same. All right, so with that being said, let's jump to the most interesting part, and let me move this to the next page, coding, right? So as we start to code, it is very important to pay attention to the naming, right? So there are like a couple things that are hard about computer science, and one of them is naming your variables and functions. So it's very important, and it is definitely something your interviewer is going to pay attention to, and so you should too. Be careful about it, be mindful about how you name things, right? So first thing we need to decide is how we're going to name our function. So we need to return a deep clone of a graph. So I'm just going to go ahead and say function clone of graph. And it's, as we mentioned before, it's going to take a node, and it can be optional. And in return, it should return an optional node, just in case if it's empty, it will return nil, right? And then we can bring up our outline of our approach, so we can reference it and write our code. So first thing, we need to create a variable to hold our visited nodes and copies of it, right? So in a dictionary, we're going to store copies of our nodes we visit in our original graph. So I'm going to say visited copies, right? And it's going to be a dictionary of int for key and for node as values. And it's going to be empty as we begin, but then we're going to populate it, right? So what I'm going to do is actually create our DFS, and let me go ahead and change the font so it does look like code. Yeah, much better. So make some space. So for our function, I'm going to name it DFS. It's going to take on the node, and I'm going to handle it in our DFS function, the edge case we've talked about before, when the graph is empty. So this is going to be an optional, and let me see. And the next parameter is going to be visited. Visited. Yeah, I'm just going to like name it shorter, not visited copies, but just visited. So it's easier to write. And then it's going to be like, as we want to change it, so it's going to be in and out dictionary, same declaration, and at the end, probably we would want to return a node, and it can be nil. As we mentioned, we want to cover the edge case in our DFS. So the first thing first, I'm going to go ahead and check for that edge case. Guard let node equals node, else I want to return nil, right? So that is done. And now let's think. So first, as I'm visiting DFS. And by the way, you want to have like a good structure, an outline of how you're gonna write your DFS, because there are a number of things you need to decide. You need to decide like during the time you implement the DFS. So you don't want to be like second guessing, like should I do it this way or other way during the interview time. It's better to have like a one outline structure to your DFS and BFSs, and just like stick to it during the interview, right? So for me, it's just first I want as I visit DFS, I want to say that it is visited, right? So I'm gonna say visited, and the way we access our dictionary is through the node val, and I'm gonna say you're gonna hold the copy, right? So I need to create a copy of a node with val. So I'm gonna use this default dictionary or default constructor we have to create a copy. So now my visited is stored and holds a copy of a node, right? And the next thing is probably I want to loop through the neighbors in a let me see, it's called neighbors. Loop through neighbors, and or one thing to pay attention to here is that this array can be actually array of optional nodes, so it can be nil sometimes. So I want to check for that. I'll just go ahead and say let, again, use the same structure as before, let nay equal nay, else and in this case, I don't want to return anything. I would want to just keep it, so I'll type continue. Okay, so that's covered, and now let me think, like, so for every neighbor of a current node we are visiting, we want to check first if let it is copy of nay in our visited dictionary, right? So I can say nay.val. If it is inside of our dictionary, it means we have already created a copy of it, and we can access it. So but for this step, it just means that we need to go ahead and get our node through this visited, get a copy of our current node through this visited data structure node.val, and say it's going to be optional, right? So I'm going to use optional chaining here and say access it array and append that copy we just got from our visited to that array. So now we have created this connection, let's say between 2 and 1. So we created a connection between copy of 2 and to the copy of 1, because we accessed 1 through our dictionary, right? And the second case is if else we don't have the neighborhood in our visited dictionary, it means we need to create a copy of it. So I'm just going to go ahead and create a copy of nay. I'm just going to name it the same way. Copy of nay using again our dictionary. I'm going to say nay.val. So this is a copy, but let me think. Actually, no, right? I can do that, but my DFS is I can actually go ahead and call my DFS to create that copy and put it in a visited, right? So I'm going to go ahead and say DFS for this nay, and pass our visited pass it by reference visited, and then yes, as I said, it's going to return me a copy of nay, and after that, I can just go ahead and say the same thing pretty much. If I need to, like this DFS is going to return me a copy of this nay, and I'm just going to say paste it as an append it as a neighbor. And the nice thing about it is this is going to be an optional, but neighbors can hold actually optional nodes. So this is going to work, and that's pretty much it, except at the very end, I just want to return, because this function needs to return something. I just wanted to return visited node, let me spell it correct, node val, and that's it, right? So this is going to return me an optional, so this matches, and then at the very end, I just need to call this DFS, but I need to call it the right way. So I'm going to pass node and pass this visited copies, and I'm going to pass it by reference, and that's it. Yeah, I think that should solve the problem. So that's it for the coding part. let's move on to the next one. It's actually very important. You want to do the dry run of your code to catch small bugs and typos before before your interviewer points it out, right? So and you lose like points for like writing buggy code, right? So you want to you want to bring it up yourself first. Say like, okay, I'm done coding, but let me first do a quick dry run and see if I made some typos or made mistakes, and like double check my code, right? So it's always good to mention that. And I cannot imagine your interview saying no to that. So we're gonna do a dry run of our code and check if we did any typos. Um, let's see. But again, for graph problems, it's kind of hard to do a dry run. It's like much easier for array problems and like string problems. But again, it's like always good to catch bugs in your code yourself rather than situation where your interviewer has to point it out for you. All right, so let's somehow try figure this out. Okay, let's say we're given this graph. Let's try to do the every step. Let's actually go ahead and copy it down here so we don't have to scroll back and forth. So and I'm gonna do comments here, so we actually follow every step of a way. Let me actually change this back to Courier. Right, so okay, we created this function clone graph. We created a visited copies. We run our DFS, and let's see. Let's go ahead in our DFS, and let's say actually we have visited, and it's empty for now. Then let's say we started at this one, right? So we called our DFS. We have value 1 here, node 1, pump, 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 and then okay, here I have one bug, so we need a space between. So in our DFS, we pass in node, we are passing our visited, which is empty right now. We check in the node, it does exist, it's not nil. We put our visited val, so this first thing we put a copy 1, right? And then we go through the neighbors. But there's no such thing as neighbors. We need to say node neighbors, right? Another one. All right, so we loop through the neighbors. We check that it's not nil. We go ahead and check if we have visited that neighbor. Let's say we are at 1 again. We looking through the neighbors. We have two options, 2 and 4. Let's say we start with 2. We check it's not in our visited, right? We only have 1 in visited. So we go ahead in this else clause. We create a copy of an A by calling a DFS. So we are calling DFS with 2 and passing this visited. And then we again in this DFS, we check that it's not nil. We put I'm just going to go ahead and do it this way. So we have visited 2, and when we create a copy, with lowercase copy of 2, and go ahead through its neighbors. We get here, we check again if we have, let's say we check in the neighbor 3, right? Or we actually can check the neighbor 1. Let's check the neighbor 1 first. We check the visited. We see that it is actually in our visited. So we go ahead and get this copy and append that copy to 2's neighbors, right? So now neighbors of 2 has, previously like it had 0 neighbors, now it had copy 2 has 1 neighbor 1. Okay, so like we're at 2 again, and we are done with 1. We go back and check the next neighbor 3. 3 is not in our visited list, so we go ahead and call DFS on it, right? So so it's nice and lined. For some reason it doesn't want to line up, but again, it doesn't really matter. We can say visited 3, copy 3, right? It's again empty. Yeah, I was right here, and here I can say we are calling DFS at 3. We created a copy, put it in our visited, and then now we are looking through its neighbors. Okay, we come back to the neighbor 3, to neighbor of 3. Let's check 2, right? Because it is neighbor of 3, right? So we checked the neighbor 3, the neighbor 2, sorry, and we see that it is already now visited. So we just go ahead and access it, its copy, and append it to visited. So we will here we append 2, and then move on to the next neighbor 4. That's how we create the neighbor 4, copy 4, and again it's going to start out with empty, but yes, Okay, yeah, so follow me alone. We are this 4, so we should say here that is we are DFS with number 4. And again, like we're gonna do we've created a copy, put it in our visited. We're gonna loop through the neighbors, check 3. We see that it is visited. We just append the copy to our neighbors, and then again we're gonna loop through the next neighbor. We see 1. Again, it is already visited, so we're just gonna append the neighbor copy, and then we are done with 4. We come back to 3. We see that like we've checked the neighbor 2, but 3 has another neighbor. It's 4, right? So we loop through this again and check if it is on our visited. It is. So we get just a copy of it and append to our neighbor. So we're gonna say 3 has a neighbor 4, and then okay, we are done with this. This is gonna return. This is gonna return our, yeah, we're done with this, and it's going to return to this call, right, DFS, when we were called here, right? So when 3 was not in our visited, we called this DFS, so it did create a copy, and we just access it through visited. We append the neighbor here with 3. 2 has 1 and 3, right? And then the same thing is going to happen for 1. So that's pretty much the dry run for our code. Let's move on to the last part. Okay, after we are done with dry run, let me also mention that the dry run is very, very important for several reasons. First of all, you can like it gives you an opportunity to double check your code and avoid small bugs like typos, stuff like that, so you don't lose points on that. And second of all, second reason why it's very important, it just verifies that your code solves the problem and your interviewer agrees that like you did actually solve the problem and get all the points, like you successfully passed this stage. Yeah, so like it just like verifies. It doesn't leave room for like second guessing. Like if for some reason, like if your approach is new to interview and he's not sure if it does actually solve the problem correctly, or like does it get all the edge cases and stuff like that. So it's always a good practice. So okay, with that being said, I think we're done with the interview portion. So let me go ahead and actually copy this implementation and go back to the LeetCode and double check myself, like to be sure that I actually did not, like I actually solved this problem correctly and I didn't introduce any bugs. Um, so like as you can see, I have solved this problem a couple times, so it should work. Yeah, let me submit. Yeah, as you can see, it is pretty efficient and like does the job, passes all the tests. So thank you for watching, and please let me know if you like this approach and would like to see me doing this same problem but using BFS. And please hit that like button and subscribe to my channel for to stay updated with new videos.